I'm Casey Papovich. I'm a professor of physics and astronomy at Texas A&M University. Primarily, my research focuses on using very deep images of the sky taken from the Hubble Space Telescope and large ground-based telescopes to study how galaxies form in the early universe and evolve to form structures like our Milky Way. Because the universe is expanding and the speed of light is finite, it's very fast, but its speed of light is ultimately finite. We never see galaxies as they look now, today. We only see them as they looked in the past. We see them as they looked when the light left those galaxies billions and billions of years ago. So when we look at very distant objects, we see them as they would have looked billions and billions of years ago. And so when we look to the most distant objects we can find, the ones that are really billions of years away, we see snapshots as they looked like when the universe was much younger. And so by studying ones that we find in the incredibly distant universe, some of the first galaxies, we can then track those objects over time as we get to more and more closer objects to see how galaxies would have formed. So one of the things that's really amazing is that when we look out into the first galaxies, the most distant ones we can see, we see that actually the nearby galaxies have structures, very mature structures. They look similar to the Milky Way galaxy. They're very smooth and symmetric, and they look very fully formed. But as we look farther and farther in the universe, out to billions of light years distance, that's when we see galaxies that are still forming their stars, still assembling their structures, and we get a snapshot in time of what the Milky Way may have looked like when objects, even before our own sun, would have formed within the universe. And then as we look to see the very first galaxies that we can find, they seem to be ablaze with star formation. There's no coherent structure. They're very irregular in appearance. And we're seeing a snapshot just as they were first forming the first stars within those objects. Using the infrared on Hubble, we actually are able to see galaxies that are completely invisible in the visible light that we can see with our eyes. So if you're using a telescope on the ground or with Hubble that is only sensitive to the light that we can see, these galaxies would be invisible. Instead, because they're expanding with the universe, their light has been stretched to the point where it's beyond what we could see with our eyes, and you have to go into the infrared to see it. And so with the installation of these infrared cameras on the Hubble Space Telescope and on ones on the ground, we're able to see the light from these very first objects. So one of the things we're very good at doing is measuring how fast objects are moving away from us in the universe. We're able to measure that expansion rate very clearly. That's simply the Doppler velocity. How fast these objects are moving away from us corresponds to a very specific, corresponds to a very specific shift in the frequency of light that we see coming off these objects. And because we know the shape of our universe so exactly now, we are able to relate that expansion velocity, how fast the objects are moving away from us, to the age of the universe when we're seeing them. So we're able to monitor that age and calculate that age very exactly. And then we know how old the universe is today here on Earth. And because we know how long the light has been traveling, and we know how fast light goes, it goes very quickly, but it's finite. It's 186,000 miles a second. We can then calculate the distance that light has had to travel in that time from that object to us, and that's how we're able to measure the distance to those objects. So the galaxies we're very interested in are the ones that have yet to achieve their mature appearance. They're ones that are still in their infant stages or their adolescent stages. And some of the discoveries we've made really seem to indicate that it's during the first few billion years of history in the universe when those galaxies grow very quickly and they mature. And so the ones we're most interested in are the ones that we can first detect maybe a billion years after the Big Bang, up to a few billion years after the Big Bang. And those distances are enormous. We're talking about objects that are between 10 billion light years away up to 13 billion light years away. And so again, we're seeing those objects not as they look today, but as they looked 10 to 13 billion years ago. We think the age of the Earth is somewhere between 4 and 5 billion years. So we're seeing a snapshot in the universe long before the sun and the Earth would have formed. So one of the great discoveries over the last couple decades has been the cosmic microwave background, which is the leftover radiation from the Big Bang itself. Today, around us, it's very, very cold. It's only a few degrees above absolute zero. But billions of years ago, say within a few 100,000 years after the Big Bang, this was the dominant force within the universe, and the universe would have been extremely hot. Now, our observations show that this cosmic microwave background was incredibly uniform, and to the point where it only deviates in 1 part in 100,000. There's small, very small fluctuations, but otherwise it's highly uniform. Nevertheless, it's those small fluctuations, 1 part in 100,000, that then cause certain regions in the universe to be slightly overdense in matter and radiation and slightly underdense in matter and radiation. And those are the seeds that then grow over billions of years just by their gravity. And gravity is something we understand very well. And so given billions of years, regions of the sky that have small overdensities of matter tend to accumulate, and they pull more matter in, and they grow larger and larger structures. And regions that are devoid of matter, that start off underdense, they become more devoid of matter as they do not have sufficient gravity to hold on to their matter, and that matter then flows into regions that do have more matter. And so those seeds that are left over from as fluctuations in the cosmic microwave background actually grow with gravity for billions of years, and they form this dark matter skeleton. Dark matter is dominating all of this. They form this dark matter skeleton into which galaxies will actually form. And so the matter that we're made of, the normal matter, the luminous matter, the matter that is in form of all the elements we see on the periodic table, they actually flow along with the dark matter. They're attached to the skeleton. They then begin to form stars and assemble the mature morphological structures we see in galaxies today. And so one of the things that we really understand, one of the great triumphs of dark matter, is that it exactly tells the story. It allows us to calculate from the cosmic microwave background how structure in the universe forms, how the skeleton grows out of dark matter over billions of years. That's something we understand very well. But how the normal matter actually is attached to this dark matter skeleton is a big challenge. And that's one of the fundamental challenges, is to understand how the normal matter actually is attached to the dark matter and then begins to form the galaxies we see and evolve to the mature structures that we see in galaxies today.